and welcome to an algebra tutorial video learning about solving linear system of equations. In this video we're going over a word problem. We're going to learn how to translate the problem, define our variables, turn it into a linear system of equations, and then be able to solve it using either substitution or elimination. Alright, let's take a look at our problem here and see what we got going on. When a boat is traveling with the current, it is able to travel 264 miles in 6 hours. However, when traveling back up the current, it takes 7 1/3 hours to go the same distance. What would the speed of the boat be in still water, and how fast is the current? Alright, let's start off with defining our variables. See what our question is here. We're asked to find what is the speed of the boat in still water and the speed of the current. So two speed things. So let's let x equal speed of the boat, and let's let y equal speed of the current of the water. Okay, the other thing we need to keep in mind is I'm noticing a trend here. We have miles, which is a distance, we have hours, which is a time, and we have asked to find speed, rates of speed, right? I'm looking at probably using the relationship that the distance you travel is equal to your rate of speed times time. This is a distance, rate, time problem that we're asked to work with. So I'm going to keep that relationship in mind as I'm piecing together some equations and trying to translate this thing in here. Okay, so if I got distance, rate, and time, and I've got speed related with my variables, hopefully I know some distances and I know some time. So let's see if we can see what we got going on here. In my linear system, we're comparing two things. In this case, we have up the river and down the river. So let's start traveling with the current. So I know I've got 264 miles. That's a time. We can put t there. In 6 hours, that's a speed. Or 6 hours, so that's a 264 miles is a distance. 6 hours is a time. Kind of mentally going wacky here. However, and what I don't know is the rate. So I'm going to put down, however, 264 miles in my distance. That's how far I travel. And it takes me 6 hours, so I'm going to put that in for time, but now I need to think about what am I multiplying my time by? Well, the rate of speed, if I'm going with the current, the speed is going to be the speed of the boat, but it's also being pushed along. The speed is increasing because I'm going with the water. The water itself is flowing, and if the boat's going with the water, their speeds are combined. So I can model the rate of speed going with the current as x plus y, the speed of the boat plus the water current pushing it along. So there we go. I use my distance, rate, time relationship to write an equation for going upstream. Now going back against the current, things are a little bit different, right? I'm still going the same distance. I'm told that in the problem. But it takes me a little bit longer. It takes me 7 1/3 hours because now I have the boat speed, but it's fighting against the current. The water is slowing it down. It's pushing it. So I have to take x minus y to represent my speed as being slowed down going back up the river. All right, there we go. We have two different equations. X and y are the same thing. And we're able to model the situation of the boat going up and down the river. All right, let's solve this thing out here now. Let's go ahead and distribute. I want to see what these equations look like a little bit differently, and then we'll decide which method might be better. So I'm going to distribute the 6. So I get 264 equals 6x plus 6y. And then I'm going to distribute the 7 1/3. So there I got 264 equals 7 1/3 x minus 7 1/3 y. All right, I think my plan, I'm noticing something here. I've got 6 and 6 for the top one. I think 264 is divisible by 6. If I check, Yep, 264 divided by 6 turns into 44. I pull out my calculator here. Yep, turns into 44. So I can rewrite that whole equation on the top as 44 equals x plus y. I just divided everything on both sides by 6. So I divided that by 6, that by 6, and that by 6. And as long as I do the same thing to both sides of the equation, it's good. Well, now my new system, I still have the bottom equation, but the equation in blue, but my red equation is now a little bit simpler, and it's now really easy to get a variable by itself. If I take that x by itself, I can get x equals 44 minus y. And guess what? I'm going to use substitution. I'm going to substitute 44 minus y in place for x into this problem right there. All right, so let's use substitution. So rewriting what I have now, I've got 264 is equal to 7 1/3 times x, but I'm substituting 44 minus y in place of x, and then I've got minus 7 1/3 times y. All right, at this point, I'm tired of the fractions. I'm tired of the 7 1/3. So what I'm going to do is multiply everything on both sides by 3, make everything bigger, because I don't want to deal with fractions anymore. It's going to give me a little bit of a headache. So now let's see what we got. 3 times 264 is going to be 792. 3 times 7 1/3 is just 22 times 44 minus y. I don't need to multiply that because it's already multiplying the 7 1/3, which is multiplying the parentheses there. And then I got minus another 22y. Okay, let's distribute the 22 right here. So now I've got 792 is equal to 22 times 44 is 968 minus 22y minus another 22y. That gives me, switch to brown, 792 is equal to 968 minus 44y. Let's subtract 968 from both sides. 792 minus 968. And now we've got negative 176 equals negative 44y. And if I divide both sides by negative 44, almost there, we see that y is equal to 4. All right, look at all that algebra work there. So what does this mean? Y is 4. Well, let's go back to what we defined our variables as. Well, y is the speed of the water current, which means the water current is 4. In this case, 4 miles per hour, because that's the units I've been working with. All right, so the water speed, I'm going to write that down. The water current is 4 miles per hour. So it's kind of moving along slowly, but moving along nonetheless. I'm still asked to find, well, what is the speed of the boat in still water? Well, let's go back to my equations here. And we've got 264 equals 6 times x plus y. Well, I know what y is now, so let's put that in and solve for x. I'm going to make a little bit of space over here. Kind of running out of room, huh? 264 equals 6 times, I don't know what x is, that's the boat speed, but I do know the current is 4, so x plus 4. All right, if I distribute that out, I get 264 equals 6x plus 24. Let's subtract 24 from both sides. So now I've got 240 equals 6x. And if I divide both sides by 6, we get x equals 240 divided by 6 is 40. All right, so I squeezed it in there, but x is 40, 40 be the speed of the boat, which is 40 miles per hour. So the boat speed in still water is 40 miles per hour. So going downstream, the speed was 44 miles an hour because you got the boat speed with the water current, but going back upstream, it slows down to 36 miles per hour because the current's slowing it down. All right, there's a good problem involving linear systems, distance, rate, time, using the substitution method. Hopefully it was a great example for you guys as you're working with your own word problems.